Oh, so before I begin, thanks to the organizers for putting this together. It's really lovely to see so many people attending from all kinds of places. That's those of you who know me, kind of, you know that I was born here sort of many decades ago, and although, yeah, no, really many decades ago. And although I haven't been around, but back then, obviously, the optimization community in India was nowhere as big. So it's good to see that there are many people not just doing optimization, but discrete optimization of different flavors. So thanks to Ashutosh, Avinash for putting this together, and I just hope that all you guys just take it off from here and sort of keep doing good work. All right, so I want to talk about nonlinear IPs, like specifically nonlinear and not mixed integer, because the ideas that I present work only in the pure integer case. But I mean, we are doing something on one side to do the mixed integer, but I'm not going to talk about that today. And the goal here is to sort of exploit structure, I mean, be structure agnostic in a certain way, but sort of use permutations in sort of a more novel way than they have been used before. And so I should acknowledge that most of the stuff was done with my PhD student who is now X. He just finished a month ago and is starting at Amazon in London and Luxembourg next week. And so here are, so some of the work is, which I'll lightly touch upon, is already published in MOR recently, and the other stuff is in the other papers. All right. Okay, so just a bit of it. So I'm looking at nonlinear IPs. So I basically have, I take a compact set and I want to optimize a function over the integer points in the compact set. And there are lots of methods. I'm not going to get into mentioning those. There have been lots of talks about spatial branch and bound, relaxations of different kinds. So you can exploit quadratic structure, polynomial structure, something else. But here the emphasis is we are going to propose new techniques which are in some sense structure agnostic for the representation of X. So for now, I'll just assume that X doesn't have a specific algebraic representation. Perhaps you can think of X as just being given by some membership oracle. Right, so I'll sort of have to do something called a membership oracle for X later on to sort of get some kind of a algorithmic routine. And our idea is to sort of look at the integer lattice. Of course, that is the Zn. I'm optimizing over the integer lattice, right? So points, integer points inside X, and use the notion of ordered sets on the integer lattice, right? So if you don't know what ordered sets are, I'll sort of define them. In a way, I mean, there is like a whole community of orders and ordering theory and so on. Okay, so the one way we are specifically going to construct ordered sets, I mean, there are many ways to construct ordered sets, right, is using what are called as monomial orders. So a monomial order is, it's a total order, meaning sort of, first of all, like an order, it's like a binary relation. So you give me 2 points, so say 2 vectors in our case. And the binary relation basically compares the 2 vectors, essentially saying is one less than the other, or the answer could also be neither is A less than B nor is B less than A. And those are what you call partial orders, right? So then they have these properties like reflexivity, symmetry, transitivity, and so on. So your standard less than or equal to order on the vector space of dimension 2 or more is a partial order. Because not every vector, if you take vectors of dimension 2 or more, you can't always say that A is less than B or B is less than A. They could be incomparable. So that standard order is a partial order, but monomial orders are more than that. So they have to be total orders. So meaning that any 2 vectors or any 2 points can always be compared. You can always say one is less than the other or not, or they are equal, obviously. And then you also need what a translation invariance, which basically just means that if you take 2 integer vectors and to both of them you add the same integer. So take 2 integer vectors A and B, and you take a third integer vector C. So if A is less than B, then A plus C is also less than B plus C. So that's what translation invariance means, right? So you basically add the same thing on both sides, and then the order relation does not change. So these things have been commonly used in computational algebra for writing multivariate polynomials, right? And so that's the standard use. I also have an example later on. And there are many kinds of those. The standard one is lexicography, which is also called dictionary order, because that's how the words are sorted in a dictionary. Right? So, and that's the one that we are mostly going to work with. And the reason we are mostly going to sort of focus our attention, because there are many monomial orders. It's like a whole family, possibly infinite family. But there's a nice characterization from mid-80s which basically says that you can reduce or essentially think of every monomial order as a linear image of the lexicographic order. And so this is really a fantastic result because you sort of go from this infinite family of monomial orders. Essentially, you can reduce your thinking to just the standard lexicographic order under some linear mapping. The only trouble, well, trouble from our perspective, not from this computational algebra structural perspective, trouble from our algorithmic perspective is that the entries of this linear image can grow exponentially, right? So for different orders, they can be like you can get powers sort of, and then you can't really use those numbers in any meaningful way. And so yeah, so here's the definition of the dictionary or the lex order. Basically, given any two points, either they are equal or you basically they are equal up to a certain coordinate, and then beyond that coordinate, sort of one entry is less than the other entry. And if you think about it for a minute, this is how words in a dictionary are, right? Sort of you sort of make sure that up to a certain coordinate or up to a certain letter, they are the same, and then on the next one, you sort of sort them. So as I said, so the whole family of monomial orders can be reduced to sort of these linear mappings, and sort of I'm going to particularly look at linear mappings coming from permutation matrices. Okay, so these are nice matrices. They have nice properties. They are all 0-1 entries. There's also the famous Birkhoff von Neumann theorem about what their polytope looks like and everything. And so when I look at permutation matrices, that means I just take my standard lexicographic order and take its linear image under some permutation matrix. Right, so what that does is I can define now my order compactly as this way. So now when I say A less than B, so in the usual case I would just say A less than B, right? But now I sort of add a permutation, say any permutation sigma of the symmetric group, and then what it really means is that permute both the vectors and then compare them in the standard order. So that's what this the effect of this permutation map is. Right, and yeah, sorry, so this is the example. So where do these things, while writing multivariate polynomials, so sort of if I have a multivariate polynomial like this, so in this case I would just think of a monomial by its exponents. So its exponents are integer vectors, right? So this monomial has, the exponents as 2, 0, 3, 1, this is 0, 0, 2, 1, 0, and then this one is 1, 1, 0, 1. Right, so sort of this, I can take these three integer vectors of dimension 4, and if I had to order these monomials, I'm asking about ordering these integer vectors. And depending on what permutation I choose, I'm going to get a different ordering, right? So under the standard permutation, this is the ordering. Under this permutation, this is the ordering. Now, why is this in the computational algebra context? Why is this important? Because sort of, I think Sanjeev talked about this using Grobner basis yesterday. So when you compute a Grobner basis, if you know what that is, it's basically a basis, but you sort of have to kind of sort your monomials in some way. And the sorting of the monomials has a big impact on the runtime and the kind of basis that you get. And there are different orders that are used, and then to determine those different orders, you kind of have to pick some monomial order. And they all have different properties of the Grobner basis. But anyway, we are not going to do any Grobner basis here, but I just wanted to sort of make a connection. All right, so what does our approximation scheme look like? So basically, okay, so take any so take any subset of the symmetric group. So this Sn is the symmetric group of n elements, which basically, that's the standard notation. That just means the set of all permutations on n elements, right? And so when I say H, H is really a subset of Sn, so it's not a subgroup. It doesn't have to be a subgroup, meaning that it doesn't have to satisfy the properties of a group, right? And so once in a while talking, I might say subgroup, but what I really mean a subset of the symmetric group, right? Because we don't use any group properties here. We don't need a closure under inverse or closure under composition or anything, or at least not for the results that we have. And so what you can do is, because these monomial orders are total orders, under every monomial order you can define a maximal and minimal element. In fact, like, because these are total orders, instead of maximal and minimal, I can say maximum and minimum, because it's a total order, right? So here maximal and maximum are the same. If you have a partial order, maximal and maximum are not the same, right? But for total orders, mul and mum are the same. So you can compute these, compute or define these maximum and minimum elements. So I'll just call them theta and gamma. So for every, so these are depending on the permutation, right? So for every permutation, I have a maximum theta and I have a minimum gamma. And then you sort of take the collections of all of these, and then you can sort of mod out some equivalence class. right? So this is what this operation, so this is like a mod operation. Basically what it means is, what can happen is, depending on what the symmetry group of the set itself is, so X itself may have a symmetry group X. So what can happen is two different permutations might give you the same point, essentially. All right, like many permutations might give you the same point. And so then you essentially mod those out, you just, because eventually you care about the point itself and not necessarily the permutations that produced it. So this modding out, so there's a certain equivalence class in there based on the symmetry group, and so then you just mod out the equivalence class, so you just basically take one sort of element from that defines one equivalence class. And then you sort of, so you have these big theta, big gamma, which are sort of collections of all of these maximum and minimum points. And then you can also define an ordered set, whatever, I'll call it script L, again, that depends on the permutation, that essentially says that X has to be between gamma and theta. So remember, gamma is the smallest, theta is the largest, and now you're just saying that X has to be between the smallest and the largest, right? X is all the points in the integer lattice between this gamma and theta. And so what can we do with these? So the approximation scheme itself is, okay, so you can define a primal side. So primal side, so I'm maximizing here for some whatever convenience. So the primal side is going to lead to lower bounds on the maximum, and the dual side is going to lead to upper bounds on the maximum. So I can take all these constructions, and sort of the blue part here leads to this primal bound, which basically just says, okay, maximize this function over all these points theta and gamma, okay? And on the dual side, I can do it two different ways. I can sort of convexify this set individually for every permutation, and then take the intersection of those convex hulls, which are going to be polytopes because everything is over pure integers. Or I could also do something which is in red here, which I intersect all of these over all the elements of the subgroup and then convexify that. And both of these, it's not hard to show sort of through straightforward sort of things that these really define bounds. In the sense, the primal bound really is a lower bound on the optimum. These dual bounds are also are upper bounds, and then this dual one is the Z bar is stronger than Z tilde. In the paper, we call them sort of a weak closure, strong closure, whatever. But so one is stronger than the other. I mean, quite simply, I mean, this is standard, right? You sort of convex hull operator does not distribute over the intersections. So that's just what it is. And furthermore, these bounds are also monotone in the subgroup, right? So basically, what it means is, as you throw in more permutations, you'll get stronger bounds. So on the primal side, if you take more permutation, you'll sort of keep improving your lower bound. And on the dual side, if you throw in more permutations, you'll keep reducing your upper bound. So obvious sort of monotonicity in, which is what you would sort of want for like a hierarchy or sequence of this approximation scheme. Okay, so yeah, so here is just a little cartoon kind of just explaining in 2 dimension what is going on. So sort of if we have sort of these black points, that is my integer lattice. My set is given by this black thing. So it's just a very simple polytope. So basically this black thing and everything inside is my set X. So I'm looking at black points inside this black set. And so there are just 2 permutations in 2 dimensions, like 1, 2 and 2, 1. So under each of those permutations, so the way the set is set up, it's a packing set, so gamma is always going to be 0. So I have theta 1 in the first permutation, theta 2 in the second permutation. And what these sets L1 and L2 look like are given by red and blue. So corresponding to theta 1, I have the set L1, which basically just means all the integer points x which are less than theta 1. Right? So those are going to be all these, so that's going to be this red set is going to be this polytope. With respect to theta 2, I'm going to have this polytope, and then I could intersect the red and blue, right? But then in this case, what you see that you basically get this hashed region, right, by intersecting these 2. Whereas the polytope of the integer feasible points is this thing inside here. So intersecting these 2 does not recover the polytope to represent all the integer points. But in fact, if I take the stronger version, then just without convexifying, if I just intersect L1 and L2, then indeed I do recover all the integer points. So in this case, sort of like these 2 upper bounds that I showed you, like the stronger one indeed is tight because you sort of recover the all the integer points, whereas the weaker one has has some kind of a gap. Okay. All right. So this part I'll talk about theoretical performance guarantees. So this first bit is about so the first thing was, okay, by construction essentially more or less, and with some arguments on standard things, these indeed are valid bounds. But now we would like to understand how good do they do in theory. And in the next part I'll talk about sort of implementation stuff and what can we do in practice. Okay, so here's the first result. So for this result, at least I have to assume that the objective function is monotone. So objective function can be anything nonlinear, right? I mean, it's sort of, but in this case, say it has to be monotone over the integer points. Now, if I pick just one permutation for my approximation scheme, then this is the approximation ratio that I get on the primal bound, right? So this is a ratio, essentially this is a ratio of how the function behaves sort of in each extremity of the coordinate, right? So sort of u is like the upper bound. It's sort of, we are assuming a compact set. So by translation, you can just assume that your feasible set is inside 0 and u. And this ratio is essentially just saying how bad does the function get at each end of each coordinate. Now we can do something something more, so that if the function is monotone but also subadditive, right? So subadditive just means, probably everybody knows, but subadditive just means that f of x plus y is less than f of x plus f of y. And this is all x, y. Okay, so again, this is not necessary. I'm not restricted to the 0, 1 case. So instead of working with subsets, you can work with all integer points. So just a standard definition of subadditivity. And so if you're wondering where do subadditive functions come in from, so one standard way is through composition, just like if you might have seen with submodular or supermodular functions. So you can construct subadditive functions through univariate concave functions. So you can, so if you take a univariate concave function g, right? So and g is concave, and g at 0 is 0 or above, then this composition leads to a subadditive function on the integer lattice. Okay, and this sort of thing also appears with submodular functions. Anyway, so subadditive functions obviously include linear functions because they are additive, but it is also a bigger family with this composition or other tricks. You can get other nonlinear functions. So when it is monotone subadditive, then for any family of permutations, right, and I'll explain what this means in a bit. So for not just a single permutation, because for a single permutation we already know that, and this is also like a type factor in general, but if you were to consider more permutations, remember as I said, so the more permutations that you get, the stronger is your bound, right? You have monotonicity. Then the factor becomes 1 over some kind of sparsity of f. So f is our objective function. So this 0th norm of f here really means the number of non-zero entries at endpoints of each coordinate, right? So you look at how f sort of behaves along each coordinate. It might be 0 in some directions, right? And so then you look at the number of non-zero entries. In the simplest case, if f is linear, so if f of x is just c transpose x, then this f0 is just the usual 0th norm of c. It's the number of non-zero elements in c, right? But with nonlinear functions, you really have to look at how the function behaves in each direction. Now, what family of permutations are we looking at? So what this criteria here really is saying is that for every index from 1 to n, there should be a permutation in the family that puts that index in the last position. Okay, so remember, sigma of n is your index in the nth last position, and what this is saying is that for every I from 1 to n, there should be some sigma in H such that sigma of n equals I. Okay, so obviously a lower bound on doing this is the H has to be of size at least n, because there are n indices, so you need at least n permutations to put each of them at the end. So H has to be a size at least omega n. So for any H, even if you go up, then there is always a guaranteed factor of 1 over f0. And so one more sort of extension to this. So this comes about from sort of like a separate paper that has to do with random graphs. But basically the connection is that, so through studying some clique and stable set type problems on random graphs, you can show that, in fact, so when you go to the randomized setting, so if you sort of say, take a problem, maybe X is a random set, you define some probability measure on it, and you want to ask yourself, so okay, here is a random 0, 1 IP, so F is not random, so F is deterministic, so the set X is random in some way with some probability measure. Okay, so what would happen to this factor? So what would happen is basically, okay, so you can, there are random 0, 1 IPs where this factor would essentially tell you 1 over n, but in fact the actual bound with high probability is 1 over log n. Okay, so in the deterministic setting, we can always show that this this sort of is going to be arbitrarily tight in general. I mean, not for, obviously not for every x, but there is sort of a worst case family of sets x where this is arbitrarily tight. In the random setting, it seems that sort of at least for very simple 0, 1 packing IPs just coming from independent set problems on some random graphs, that you can essentially go from n to log n with, again, with everything is high probability in that regime. Okay, so is that, so any questions here? Maybe let me pause for a moment or so. Yeah. Yeah, I mean, okay, I mean, this is a completely separate paper. There's lots of concentration measure there, stochastic analysis, and I mean, this log n bound is one of it, and there is another bound, but yeah, I just won't get into, I'm happy to, yeah, talk offline. Yeah, but there's a lot of concentration, concentration measure type results. Okay, so for 0, 1 problems, there are like some tight guarantees, but again, the tight guarantees come at the expense of really sort of enlarging your set of permutations, because, so previously I talked about single permutation and permutations of size linear at least, and now sort of I'm saying, okay, what if I were to really incorporate many permutations in my approximation scheme? How far can I get? Now for 0, 1 problems, we can show tightness under sort of some structures on the sets of permutation. So these are both on the primal and dual side, right? So I purposely kind of took out all the notation and just tried to put it in words to make it as simple as possible. But the idea is when you have a 0, 1 set, and also the crucial thing that the objective function should be extremal. Extremal in the sense, again, it's just a generalization of linear functions, meaning that when you optimize the function over the polytope of integer points, it sort of it achieves the optimum at an extreme point. Because in general, when you have convex or nonlinear IPs, right? So maximizing the objective over the integer points is not the same as maximizing it over the convex hull of integer points, right? If the objective is linear, of course they are the same, but here we have nonlinear objectives. But there are certain functions where this is true. So for example, if your function f is convex, right, we know that convex functions sort of go to the extreme points over compact sets, right? So that's what is meant by extremal here. When you optimize it over the polytope, it should go to the extreme points and not anywhere else on the boundary. So then you sort of, if you pick your permutation sort of subgroup such that you have at least one monotone permutation for every now really maximal point. So here it is really maximal because it is maximal under this partial order, right? So I cannot say maximum here because this less than or equal to, as I said, is really a partial order on the integer lattice. And on the relaxation dual bound side, you can do some similar things and you can say similar tightness guarantees. Now one thing here, so what are these permutations? So a monotone permutation is basically just a permutation that that puts zeros before ones, right? So if I have a vector 0, 1, 0, 0, 1, then a monotone permutation, so if this is x, then sigma dot x should give me 0, I should put the 3 zeros before the 1. And the 2 ones are sort of, or between the zeros is sort of, you have a cyclic group, you can do whatever you want, right? So that's what I mean by monotone permutation, that you have to permute x in such a way that the elements are sort of monotone. Okay, so so I have probably 10-12 minutes or something, right? Yeah, so maybe yeah. So let me go over, because I have like some complexity stuff and stuff, so I'll skip. So there are some implications of these tightness results to sort of representations of the Pareto. For example, we can so you can sort of, for packing and covering type 01 IPs, you can sort of get again this sort of, from a covering formulation you can go to sort of a slightly general way with all kinds of permutation stuff, and even for like say some packing 01 IPs, you can even construct like an extended formulation using these minimal maximal elements. Like for example, like the stable set Pareto, or for an independent system, you can get an extended formulation through this. Anyway, I won't go into the details. I'm happy to talk offline. So a little bit about algorithms. So the first thing about algorithms is complexity. So what I said initially, sort of, okay, this is like a general approximation scheme, right? So I hesitate and won't and shouldn't call it an approximation algorithm, because it's not polytime, right? In general, at least. So it's just an approximation method, approximation scheme, framework, however you want to think of it. Right, and so our bounds, so essentially we care about the primal and dual bounds on the optimum Z star. To compute these bounds, we have to compute the minimum and maximum point for every permutation or for a subgroup. And even if every point can be computed in polytime, the bounds can still be hard to compute. All right, and so even for packing, so for packing and covering polytopes, what happens is you give me a sigma, I can compute for that sigma, I can compute the minimum and maximum easily. But then the bound with respect to the entire symmetric group is NP hard. And in fact, for the relaxation, the bound remains NP hard, not just for the entire symmetric group, but even if my subgroup has linear size. Okay, so the entire symmetric group obviously is n factorial size, but even with linear size subgroup, the bound would remain NP hard, even though the computation of each point itself is very simple and polynomial time. So that's in some sense a bummer or negative result, that actually computing these bounds remains NP hard, but we are in a MIP workshop, everything is NP hard, and that doesn't stop us from doing all the interesting things that we do. So, so there is some hope coming in on future slides. Right, so one thing here, there's connection. So we also have a characterization of showing when these computations really are NP hard. And it connects to the question of integer feasibility. So you give me a set X, maybe through some membership oracle, it's inside this box 0U. And I ask the feasibility question, integer feasibility question, you give me the set X, and you give me another box P, and then the decision question is there an integer point inside X and B? Okay, so X itself, my original X itself might be integer feasible, and maybe that's easy to check. But I can now give you any arbitrary box and say intersect X with that box, and now tell me, is there an integer point inside this? And that I don't know the answer to, even if I know the answer for X. So that's the question. And the statement is that this basically, so the complexity of this question characterizes the complexity of what I want. Okay, so on one hand, if this feasibility question is NP hard for some box, then the computation of the minimum and maximum points will also be NP hard for some permutation. And this first part we show through reduction from Hamiltonian cycle on graphs. So that part is interesting, but the other part, probably at least for me, was more interesting in the sense this is also a characterization, meaning that the computation of these points reduces to this feasibility question. That means that this computation is NP hard only if this question is NP hard for some box. Okay, so there will be sort of sets where this would kind of tell you sort of what the complexity of computing these bounds would be. And the second part, this only if part, is through some sort of a bisection argument through each coordinate, and you sort of keep shrinking and you sort of keep shrinking the box along each coordinate, and then eventually you have to show that you shrink to a single point, and that point is indeed the optimum that you're maximum or minimum you're trying to compute. Okay, and so in this part basically, so as I said, so there are indeed some sets where you can, regardless of this complexity stuff, you can do closed form computation, right? So the first kind of set is these polytopes, which are sort of just a slight modification extension of packing and covering, where so your linear system can be partitioned into plus and minus, right? So you have your A matrix for the linear inequalities, and the A matrix can be partitioned into plus elements and minus elements. I mean, and you allow zeros. Zeros are okay. But basically there is no column that is a mixture of plus and minus. Every column is only plus or only minus. And then you can do this through a greedy recursion. With the same motivation, we can show it for sets that are defined by quadratic inequalities. And these don't, so here this, when I say Q greater than 0, this does not mean PSD. So this is like element wise. So Q is a non-negative matrix, right? Like element wise, not in the PSD sense. So these could be obviously non-convex quadratics in general, because Q may not be PSD. And but even for such a set defined by possibly non-convex quadratics, we have a closed form formula for these maxima and minima under each permutation. And I'll talk about it with experiment, how we use these. I don't want to put the formula because there are like square roots and all kinds of ugly things. Those details are in the paper. And the third one is sort of connection to COMBOP, which kind of also makes sense, because the first time you sort of think of, say, permutations and polytopes, so those who sort of work on matroids and COMBOP, kind of the permutahedron or polymatroid immediately comes to mind. So through classical results of Edmonds, you kind of know that if you have this polymatroid for submodular functions, there is a bijection between the extreme points of that polyhedron and the symmetric group. Okay. And so then you kind of wonder, okay, what if I were to take this set, which implicitly has every sort of this point in bijection to the symmetric group? So what does that mean for my maximum and minimum points? And so then even for those sets, we can show that what the bijection looks like for us. So it's not the same bijection that you would have in the Edmonds sense for those points to the symmetric group. But in a sense, so if you take a point in the polymatroid, if the Edmonds bijection tells you it is sigma, then our bijection is the inverse of sigma. Okay, so the correspondence. So inverse of sigma is just basically, yeah, it's sort of the inverse element in the symmetric group. Okay, so these are sort of explicit formulae. So now going sort of ahead a bit to sort of what we can actually, basically what can we do with these? I mean, so there are these guarantees and there are sort of tightness factors and sort of things that you can compute, but sort of one of the questions is, hey, can you actually use this? Because sort of what I'm saying is, okay, there are lots of classical and new methods that do all kinds of stuff with quadratics, polynomials, other things. So why should this method be of any interest if you're sort of proposing a new technique to do things? So then the question is, okay, how can we use this in practice, right? So how can you make this approximation scheme work in practice? Because the inherent bottleneck is, well, you can work with, first of all, you can work with a single permutation, but it is not clear what that permutation should be, right? So you give me a problem to solve, and then I'm, okay, what sigma should I use? There are factorially many to choose from. So what makes sense to be a good sigma? So that is sort of one practical consideration. And the second one is, how do you actually sort of implement this or even do the computation of the maximum and minimum points? So one method that we used is what we call lift and project, which has nothing to do with lift and project from cutting planes, but the point is we create an extended formulation and project it. So it's like lifting and projecting. So the idea is, if you give me a polytope, and this kind of idea works even for conic representable sets, right? Because ax less than b, instead of the less than, you can just do it with respect to a nice cone. But anyway, let's just take polyhedron for now. So every sort of bounded polyhedron, you can write it as a projection of a packing polytope with one single linear equation, right? And this is a constructive thing. I mean, it's straightforward, well, straightforward. Basically, you look at the elements of the matrix A and take like some absolute maximum and infinity norm and so on. So then the idea is, this suggests it, so why is this important? Because a couple of slides ago here, so I showed you that if my polytope is packing type, I can do this computation explicitly and very quickly in sort of almost linear runtime. So using this lifting idea, the goal was, okay, first of all, you give me any polytope x, I will construct its lifted formulation. Then I'll use my formula just for the packing polytope part of it. And in the last step, I'll round that solution by projecting or rounding it onto the hyperplane. And that is obviously again a bottleneck, right? Because here I somehow have to, so this computation is explicit, there's a formula, it's a linear runtime, so this is easy. But then to get correctness, because remember the set is the packing polytope intersected with this equation. So I somehow have to round this point onto the hyperplane, right? So you can think of many ways of rounding it. A generic way is just set up a projection problem, which is a quadratic IP and it is a bottleneck. I think maybe Swati was saying yesterday, in her also there was like these projection problems can be, they are convex quadratic, but they are IP. And in practice, yeah, solvers do stumble and are not as quick as you might think they should be. Okay, so this is one approach. And again, so there are, I'll just gloss over this. I mean, there are various ways that you can do all kinds of like implementation tricks, right? You can do it in a heuristic callback. You can just try to polish off a fractional solution. You can do other things. I mean, what can you do with this scheme? You can either try to round a fractional solution in sort of in a practical way, or you can also try to improve on an existing solution. So somebody gives me an integer solution either through the solver or through specific to the problem, and then you apply your approximation scheme on top of it and try to improve on that solution. Okay, so what happens, so I'll just talk very briefly because I should finish I guess in 2-3 minutes or so about experiments. And so what happens, so we did 2 sets of experiments. So first of all, so although sort of the whole idea and framework and scheme works for nonlinear IPs, so the first step obviously what happens with linear IPs, right? I mean, if it is completely hopeless for linear IPs, then why even bother going to the nonlinear world? And so it is not completely hopeless for nonlinear IPs. So this is just a summary table. So essentially, so we compared against standard solvers. So there's Cplex here, and before somebody asks why Cplex in 2024, I'm going to say that we tried with Gurobi as well, and more or less was the same. So yeah. I mean, I think Cplex originally because my student was more comfortable with the concert library interface, and yeah, that was the first thing. But thanks to us, I mean, Gurobi also wasn't doing, the numbers weren't starkly different. I hope there is nobody from Cplex here. All right, so so yeah, so in terms of average, so these are sort of comparing the different all kind of combinations, the different implementation tricks that I mentioned before. Do I round? Do I polish? Do I take the last solution? Do I put it in a heuristic, in a callback and greedy, or lift and project and this and that? And so essentially sort of, yeah, so in terms of, so one key takeaway is like doing all of these approximation schemes does come, like for example, if you look at CPU times, on some of these methods you can spend a lot of time. I think these are basically geometric averages, probably over 100 instances or so, right? I mean, we sort of constrain to these non-trivial instances. And so you do spend considerable amount of time on some of these methods at least. But then you do gain sometimes quite a bit in terms of primal bound. So you're able to find better solutions than what standard solvers could do. And here I think, yeah, so these are also profiles here. So I think the left one is with respect to the actual value of the bound, and the right one is with respect to CPU times. And so you can almost see it flip, like some of the methods that are sort of, I mean, I won't go into the details. I mean, these are again all the combinations. So the standard Cplex would be sort of like this pink profile, I guess. And the other ones are one of our. So for many of these, yeah, you do end up getting much better solutions, but then of course it sometimes does come at the expense of your spending a lot more time on your method itself than possibly doing some of the other heuristic methods inside Cplex. So we did try it with binary QPs as well, or binary QCPs, I should say. So I think the objective is just linear, and you have like a bunch of quadratic constraints. Right, so I think we kept these to be 0, 1 because we knew that the MIP solver would sort of linearize them and then possibly solve it in a linearized way, or just treat it in any other way it would want. And but the criteria was, these were randomly generated. The criteria was that sort of the Q matrix has to be element-wise non-negative. And again, this because as I showed a couple of slides ago, so for these kinds of quadratically defined sets, we have a formula that computes the maximum and minimum for every permutation. So we have a closed form computation. So we apply that with all the other tricks, and then essentially what happens is sort of go into the details, but essentially again in terms of the picture changes a lot with the density of the quadratic matrix, which is I guess not surprising in the quadratic world, but and the gaps are sort of more or less closely matched also in terms of CPU time. Okay, so I think that's it. Yeah, that's it.